In this lesson, we're going to learn how to separate two solids with different solubility characteristics using fractional crystallization. Consider two fictitious ionic compounds, QX and GY, that have different solubilities in water. The solubility of QX also changes more with temperature than that of GY. We're going to use that fact to help with the separation. For our example, we'll dissolve a 100-gram mixture of 50% QX and 50% GY in water at 100 degrees Celsius. Water doesn't boil at 100 degrees Celsius when ionic salts are dissolved in it. We'll learn about boiling point elevation in another lesson. Our 100-gram mixture will completely dissolve in 100 grams of water at 100 degrees Celsius because its components' concentrations are both below their limits of solubility. QX has a solubility of 63.4 grams per 100 grams of water, and we've only dissolved 50 grams of QX. GY has a solubility of 75.2 grams per 100 grams of water, and again, we've only dissolved 50 grams of GY. The salts are relatively easy to separate because the solubility of QX is far more temperature dependent than the solubility of GY. As the solution is cooled, GY should remain dissolved because it remains relatively soluble. QX, however, will precipitate as a solid because its solubility decreases rapidly as the solution is cooled. Let's look at what happens when the solution is cooled to 0 degrees Celsius. Water that contains ionic compounds in solution won't freeze at 0 degrees Celsius because ionic compounds in solution lower the freezing point of the solvent. Since the solubility of GY is still 52.4 grams per 100 grams of water, and we only have 50 grams of GY in solution, it will all stay in solution. The solubility of QX, however, is only 5.1 grams per 100 grams of water at 0 degrees Celsius, so the remaining 44.9 grams of it will precipitate as a solid crystal. At this point, we can calculate both the percent purity of each salt, or what percent of the product mixture is the actual product, and the percent yield of each salt, or what percent of the product was recovered once it was purified. Let's look at the QX that precipitated from solution first. Since the GY was still in solution below its solubility limit at 0 degrees Celsius, none precipitated. That means that once the precipitate is separated from the supernatant, or solution where the precipitate is sitting, it'll be 100% pure QX. To get 100% pure QX, however, we had to sacrifice some of the yield. According to its solubility, 5.1 grams of it remained in solution with the GY instead of precipitating. That means that only 44.9 out of 50 grams, or about a 90% yield, was obtained. Now let's look at the GY. All of it stayed in solution because its solubility is 52.4 grams per 100 grams of water at 0 degrees Celsius. Once the water is evaporated to leave it behind, the yield is 100% because we recovered all of it. The purity, however, is not 100% because there was still some QX dissolved. Out of the 55.1 grams of dissolved material recovered by evaporating the water away, 50 grams are GY and 5.1 grams are QX. That means that the purity of GY is only 50 grams out of 55.1 grams of product mixture, or 91% pure GY.